what we're going to be going over here are Lagrange multipliers, and we're going to look at these Lagrange multipliers in terms of a shadow price here, and also how they compare to the directional derivative. And we're going to be doing some Lagrange calculations, and we'll also look at it from the visual perspective here. So what we're going to be looking with the Lagrange multiplier, we'll do it in terms of the production function, which is really similar to the Cobb-Douglas production function. Okay, so this is what we're going to be doing here, and we'll go over these Lagrange multipliers here. So what we're going to have here when we're talking about our production function here, we're going to have some revenue portion here, and I'm showing here $1,400. That's our unit price here for the product we're producing. We take that times some material and times some labor quantities here and raise to some exponential amounts. So what we do here, this revenue here, and we're going to be looking at it in terms of the partial derivatives here, or the gradient. That's where we have our maximum output here. So when you're dealing with these Lagrange multipliers here, you're going to be looking at them in terms of the gradient here, or the change in our production function here. So we're going to have our revenue portion here, and that's going to be equal to, and this is where that Lagrangian comes in, this Lagrange multiplier here, that Lagrange multiplier here times, again, and it's going to be the gradient or the partial derivative here of the cost portion of our production function. And I'm just showing here the cost portion here is 350 M. That's a unit price for the material for this product, plus 200 L. That would be the labor price for manufacturing this product here. But we're also going to add in here this cost constraint. We'll be looking at several different cost constraints in this problem to get an idea what how the Lagrangian works with the different cost constraints. And we'll just, for start outs here, I'll just look at a $40,000 cost constraint. Okay, so what we've done here, we'll look at it pictorially here, but we've got our production function here, our revenue portion here, equal again to the Lagrangian here times the cost portion here, and that would be the partial derivative or the gradient of each of those. So what we're looking at here, our revenue here, the gradient or the change here in our revenue equals the change in our cost here, and they only differ by a scalar amount, this Lagrangian multiplier here. So if we look at it in terms of pictorially here, I've got this blue arrow here, blue surface here with those red lines here. That's our total production function that we're looking at here. And what these red lines here are isoquant lines. And what we're doing here with this Lagrangian here, we come up against a cost constraint here. So I'm showing this cost constraint slicing through my production function here in this vertical one, and it's that mesh surface that we're looking at here. So what we're doing here, we're based on our production function, we're going to come up with the optimal amount here for our output here, our maximizing our profit essentially here. So we're going to come up and we're going to bump up against that cost constraint, and remember that's showing here the 350 M plus 200 L minus 40,000. So that will really come up to, they have to balance out here, and they have to be, the material and labor here have to equal the cost constraint. We only can spend 40,000 here on material and labor. So that's what we're talking about. So, okay, so what we're going to do here when we're talking about those gradients here, the revenue portion here, and remember these gradients here are perpendicular to our isoquant line. So they're perpendicular to it, but the gradients here, the revenue portion here, and then our cost portion here, those partial derivatives here, they're really parallel. So that's the key that we're looking at. And again, we're looking at, in this graph here, we got, or plot here, I'm showing labor increasing this way and material increasing this way, and then our output would be along our vertical axis. Okay, so moving up over here, now we'll just get a top view of what we're looking at. So we're going to be looking at several different points here of output or that we're looking at, and we're going to tie in that Lagrangian to those different points. So we're going to start out with very low output here. Cost, this is where the cost constraint would be, like $4,000, and then we're going to work our way up here. And actually we're going to look at four different different cost constraints. So what we're going to do is we're going to follow up a gradient path here. And what I'm looking at, this top view here, those are really our material and labor here. These these yellow vectors that are pushing out here, that's really our revenue and our cost. I'm overlaying each of them here, but what we're going to be looking at is the change in slope equals our change in gradient here. Okay, so that's looking at it on top view, and then looking into it, moving over here, you can get an idea what we're looking at. Here's our different output points here. I'm going to add one more in here, but just showing it. These red dots here, that's our output here. And what we're talking about, because when we're looking at the gradient, we follow along our gradient path here. And that gradient path on our cost function, that's where we have our maximum output, or maximum profit, or maximum output, however you want to look at it. Okay, so what we have to do here, just before we get into comparing our Lagrangian here, first off, we go through these different steps. So first off, you have to set up your Lagrangian equation here, and I'm showing that here. Here's our revenue portion. That's our output portion that we're looking at. And we would subtract from it our Lagrangian multiplier times our cost constraints. So that's the artificial variable that we're putting in here, and we'll be able to determine that here based on our Lagrangian equation. So we take our Lagrangian, or the lambda term here, times our unit cost for material plus a unit cost for labor, and then remember we have to subtract out our cost constraint here. So that's what we're talking about for our Lagrangian multiplier here. Okay, so then the next thing we have to do here, we have to find a gradient, or take the partial derivatives here of this Lagrangian function here, and we have to do that in terms of material, labor, and also our Lagrangian multiplier, or our lambda. Okay, so we would do that here, and then we set each of these partial derivatives equal to 0, and we solve our set of equations. So we end up with three different variables: material, labor, and then this artificial variable Lagrangian here. And based on taking those partial derivatives, we're going to come up with three different equations, and three different variables are unknown. So then what we do here is we take the gradient, or the partial derivative of each of those, set each partial derivative equal to 0, and you solve the set of equations. I don't know if I already mentioned that. This is where the revenue and cost have equal slopes. So what I've done here, just taking our Lagrangian, I've done it in terms of our material M here. And you can see here with that partial derivative, this Lagrangian is sitting in here, and that's sitting in at the unit cost here, the material. And again, you can see that's subtracted here from the partial derivative here of the revenue portion here. And then we set it equal to 0. And then the same thing here for our labor portion. So if we took our labor in terms of our Lagrangian, took the partial derivative here, and then we'd have that labor cost here on a per unit, subtract that on a per unit basis times the Lagrangian here. And then for our cost, it's just taking the material and labor unit prices here less the cost constraint that we have here. And we're going to be looking at several different cost constraints here. So what we have is three equations here, three unknowns. And incidentally, you would do this here with, in this case, I use MapleSoft to set up my equations and do my partial derivatives and such. So what you do here, these equations that we have here, these are also the gradients, because we're just taking the first partial derivative, or the first derivative in terms of material, labor here, and then material and labor, or then our Lagrangian multiplier over here. So what we would do here in this case, just for our example here, that based on our 40,000 here, we would have had a solution here of so much labor, content 0.78 fractional units here, material 78.049 for material, or for labor, material 69.68 here, and then the Lagrangian, that artificial variable, this is what we're going to, it came in at 0.96, or less than 1 here. So what we're going to do here, we'll look at a few different cost constraints here, and based in how this Lagrangian fits into, and I'll get an understanding of what that Lagrangian is doing. So okay, so now let's go on and we'll do our calculations. All right, now looking at our Lagrangian multiplier, what I've done here is I've taken this production function here and I've laid it out in three different dimensions here. So we got our material and labor shown on our horizontal axis down below, and then we have our output Q here, or our revenue or our profit shown along our vertical axis. So what I've done here is I've plotted out this gradient path here. Now remember, the gradient path, that's the path here of our maximum output or our maximum profit as we follow along our different combinations here for material and labor. So what I'm showing here is really 4 different points here. We're going to start with, let's just start at our first constraint here, where we've got a $4,000 constraint here on material and labor, max we can spend. So what we're looking at here is where we got this Lagrangian multiplier at 1.462 here, and that's the greatest Lagrangian we have here for this, in this case here. So you can see it's very steep here, our gradient, or our gradient vectors between material and labor. We're getting our maximum, earning a lot of money at this point here on unit input for material and labor. Okay, so then as we move up here, we're going to move up to the point here where we got a $33,000 cost constraint here, and it's represented by the little yellow ball. Maybe I could back it off here. And this is where our Lagrangian is at 1.0 here. This is where we have sort of a break-even point here. Up until this point, we have a Lagrangian that was greater than 1 here, and then after we get up to this Lagrangian where the Lagrangian multiplier here is 1, and then after that it reduces or tapers off here. So that's the point here, or sort of a break-even point here. So what we're looking at for this first point here with the Lagrangian at 1.46, we're just saying $1 in here. If we invest $1 into our production function here, and we're going to get out $1.46. Okay, so this is where we got our steepest slope here. So what we're looking at is really the slope here. It's going up, and then as we move up along our gradient path, it starts going down. Okay, so at 33,000, we got our Lagrangian here at 1. Then moving up to our next point here, I've set the cost constraint at 40,000. That is, we can spend a maximum of 40,000 here for material and labor. This is where the Lagrangian goes down to 0.966. And then moving down our gradient path here, we get to a cost constraint here where $100,000 we can spend on material and labor. And based on our production function here in calculating our Lagrangian, this is where we're going to get our 0.811 here. So what we're saying here, when we get to this point here with our cost constraint at 100,000, we're putting in, for every dollar we put in, we're only getting 82 cents out here. So the point is, you want your material and labor content to get for $1 in, you actually want to put in less than 82 cents here, so in order to make a profit. And we'll look at that in terms of our shadow price. Okay, so you see what's going on here. Very steep slope here in the beginning. We have that large Lagrangian. Then as we move along our gradient path, we level off here, and then we move down it here, and we're getting our lower Lagrangian values here. So that's the pattern we're following with this production function. So let's go up here and look at it in terms of just looking at it in a table here. So what I've got it laid out here, I've got the Lagrangian multiplier here. Here's our cost constraint and our revenue here. That's based on this production function here. This is the revenue portion here. And then the difference between our cost and revenue would be our profit here. So just looking at our Lagrangian here, where we had that 1.462 cost, we can only spend 4,000. Our revenue would be 71.32, so profit 31.32. Okay, easy enough. Then we get down to our break-even point here, where the Lagrangian multiplier is 1. Our cost constraint 33,000. Our revenue would have been 40,250. So the difference gives us a profit of $7,250. And this is what we're looking at when this is where we max out here on our gradient path here, maximum profit. So then we move down to our next cost constraint. That was what, 40,000. We had a multiplier of 0.966. So our revenue would have been 47,125. Subtract our cost of 40,000, we get a profit of 71.25. So you see it's already dropped here. And then at that last cost constraint, 100,000, our multiplier is 0.811. So our revenue would have been 99,980. So this is where we have come up against the loss. This is where we begin to make a loss here. So the difference, cost is greater than our revenue by $100. So you see what's here, just following our trajectory path here. So maybe let's go back and look at it in terms of our 3D here. So this 7120 or the 7250 here was with that Lagrangian here at a multiplier of 1. And then we got the 7125 here, Lagrangian 0.96. And then we get down to our loss here, where Lagrangian multiplier is 0.811 here. Okay, so you see the pattern that's going on here. All right, so if we go back up here, what we're saying here at these two different points, A and B here, Lagrangian here at 1.4 1.46. We're just saying, say if we put in $100, we take that times the Lagrangian multiplier of 1.46 here, 2, and we're going to get an output here of 146.20 here. So you see that's how the multiplier works. So looking at point B here with 9.966 on our Lagrangian, say we put in 100 here, then we take that times the Lagrangian multiplier and we're only going to get $96.60 out. And that's all based off our production function here. Our revenue gradient, remember that's that first partial derivative here in respect for the revenue portion, and then our cost portion here, which I didn't show in. I should have included the 40,000 or whatever. We'd have to subtract out whatever cost constraint we have. Okay, so that's looking at our Lagrangian table form here with our Lagrangian here as it moves down. You see, we start out with a high value here with a very low cost constraint, and then it moved down and down when we had the higher cost constraint. And likewise, our profit maxed out here at Lagrangian 1, and then we went down here. Okay, so let's go over here and let's just look at it in terms of a 3D here and just look at 2 different points, get the idea about the shadow price again here. So that first point here, $4,000 constraint, we had the larger Lagrangian 1.462. And then let's just say we move to this other one here, the $40,000, 0.966. So our shadow price, what we're saying here when we had that Lagrangian at 1.462, so again, we got $1 in, we get $1.46 out. So really what you're saying is here, if you pay less than $1.46, you're going to make some profit here. You're going to get, you want to get ultimately just put $1 in and then you get $1.46 out. So if you look at it over here with the lower Lagrangian multiplier here, where we leveled off here, and you can see, again, you can see I've got the plane showing here for our cost constraints is kind of level here, and then where we start out, we've got our gradient vectors here, those first derivative vectors here, where we very steep here, and then we leveled off here. So if we look at it again in terms of this 96 cents here, or Lagrangian of 0.96, $1 in, and you're only going to get 96 cents out based on our production function, and with that cost constraint here, 40,000. So in this case, you definitely want to have to. If you pay any more than 96 cents, you're not going to be making as much money here. You're going to sort of be, you'll be making some profit, but in this case, but your input is greater than your output. So really, the shadow price here, you determine your price based on that Lagrangian, and you have to pay what you have to pay here in order to earn a profit here. Okay, and if we gone back up over here, just looking at those gradient vectors, I got them laid out here, and I got it laid out here where I got the cost constraint, the gradients here for cost constraint for labor and material, shorter than our revenue or our output here. So our cost constraint coming in here. This is the case here we're going to be looking at just to get an idea what you're talking about, that scalar difference, because you have these 2 different sets of gradient vectors, one for your cost constraint and one for your revenue output. And this is the case here where I got the cost constraint would be low. So you can see the labor and material here for the output versus our inputs or our cost constraint here. You can see you can just see the scalar difference. That's the Lagrangian multiplier that we're talking about here. This is the case where our revenue output is greater than our cost constraint, where we would have had that higher Lagrangian here. We're going to have that difference. But as we move down along our gradient path here, actually our cost constraint would be flipping here. Our cost constraint would have the larger vector here, and then the revenue would have the shorter vector. They just switch around here depending on that Lagrangian multiplier. But that is the scalar difference that we're talking about, and it's in terms of those gradient vectors here. Remember, those are the partial derivatives here of that production function. So then finally, just looking at it here in terms of a directional derivative, try to tie that in. And remember, the directional derivative is change in unit output, or the slope that we've been looking at here. So here's our production function, and then we would have had some constraint amount here. So what you're doing here is just taking that, again, just that partial derivative with respect to material and to labor of the entire function here, and you're going to come up with some gradient here. So just looking at that first constraint here, where you stuck in that $4,000, we'd had labor content of 7.8, material 6.9, fractional amounts here, and then that Lagrangian would have been 1.462. So if I put that in, put the gradient vector, if I put those quantities here that I have here into my gradient here for material and labor, I would have a gradient vector here of 161 here for material, 0.78 here, and then for labor, 0.92 here, 44 here. So that's what we're talking about. Let's go over here. That's what we're talking about, these gradient vectors here. I'm just showing it here on our revenue portion. Here's our labor, and here's our material here. And this is really the output that we're looking at, this red one. Yellow ones here are material and labor. Those are those gradients here. And then the red one is this. And then you also have to, for the directional derivative, you have to take the unit between unit function here, or we have to unitize here those two different vectors that we're looking at. We'll not get into those, but you take them times the unit vector here, and that gives you your directional derivative. So if you unit vector here for material times the gradient here vector for material. Now remember that this gradient vector here is material and labor, both of them. It's a combination here of those two. Okay, so the idea here is, and then we take those unit amounts here times material and labor for each one of them has a different unit gradient here. Material in this case would have been 0.87, labor 0.50 here. And that's really based on taking it's the combination here, material and labor here, those different quantities we're looking at. We just unitize those, not going to get into those. So the idea here, here's my Lagrangian 1.462, my gradient 186.32. And then moving down to that other point here where we have the 33,000, so I got a labor content here 6.6 or 64 and material 57, those fractional amounts. Here's the Lagrangian at a break even or a 1 here, exactly 1. So here the gradient vector, you can see it's almost 0 here. Where our gradient, we're not really, we're leveling off here. This is where they're balancing out here. And then the unit gradient, that's again depends on your material and labor quantities here. Incidentally, that's just taking the well, anyway, that's coming up with the unit amount here for material and labor. You can look at that here. So you take that again times your gradient vector, and here's your directional derivative here is 0.05, or essentially 0 here. And that equates to a gradient here of 1 here. So your directional derivative here, your unit output here, your change in slope here is exactly at approximately 0 here. And then if we look at that next point here where we had 40,000 here, our labor would have at 40,000 here for cost constraint, 78 here for labor, 69 for material or fractional amounts, and this is where the Lagrangian went down to 0.966 here. Now this is where you can see, again, you take that times, and you can see the gradient vector is negative here for both the material and labor, and then the unit gradient here, take times those amounts, and this is what you get your directional derivative. This is where it's going negative here. This is where our output is starting to go down here, a negative point. So this is where our Lagrangian was at 0.966. This is where we're getting that gradient here derivative at a lesser amount. Up above we had it where we have a gradient was 1.0. Our directional derivative or gradient derivative here would have been 0. And then finally, if we get down over here where we had that $100,000 cost constraint, here's our gradient vector. You can really see it turns negative. 0.63 here for material, minus 36 here for labor. Take it times its unit amount here, and this is where you're going to get gradient or your directional derivative 0.7290 here. So this is the case where our unit output is decreasing based on the input. Okay, so we just went over some numbers here to look at get the understanding here of with this Lagrangian multiplier and how it worked here. And I just summarized it here at the end with the directional derivative just to make that comparison. So in this case where our Lagrangian went down here, our directional derivative went down as well here. And then this is the case here where we just had that started to show a loss here at that point. So our gradient derivative here, or directional derivative here, was negative, in this case 0.72. That would be the unit output or the change in slope. Okay, so that'll summarize our discussion.